Hi all. See that in that particular problem we are having a function fx and we have to test it that how many local max and local minimum is there inside the domain, right? Domain means here obviously see that it is -3 to 2. So what is happening after that we don't care because our function is defined only between -3 to 2. So let's write down the function here first, right? So what is my function? Let's go ahead. So here I write down that function definition first, fx that's equal to 2 plus x whole cube, where x belongs to -3 less than x less than equal to -1, and it gives me that x to the power 2 by 3 when it lies between -1 less than x less than 2. Now if I differentiate, right, let's go ahead and differentiate it part by part. So f dash x becomes 3 multiplied by 2 plus x whole square, which gives me that -3 less than x less than equal to -1, and it comes back through that 2 by 3 x to the power -1 by 3, and it lies between -1 less than x less than 2. Okay, so the differentiation is done. Now observe one thing, right, that f dash x is always greater than 0 in the interval -3 to -1. So therefore we'll say that f dash x is greater than 0 or maybe greater than equal to 0 for the interval -3 less than x less than equal to -1. So f dash x must not have a local max or mean here. So we don't have to consider for local max and local min. See that if I substitute at x equal to -2 here, obviously see that f dash x equal to 0 in this point. So that -2 will be the saddle point. It cannot be the local max or local mins, or it will be the saddle point. So if you plot, the change of the function will be so smooth that in that case we'll call it as a saddle point. Okay, the sign change of f dash x is not done in that particular zone. Okay, so that's it. Now see that obviously the other part is left, right? That other part is that 2 by 3 1 by x cube. Now see that also f dash of 0 must be equal to 0, right? Why? Because in f dash of 0, 0 lies between in the -1 and 2. So 0 I have to use the second definition. In the second definition it is 0. So therefore it implies that x equal to 0 is a critical point. Okay, but that's not it, right? We may have some other critical point as well. Why? It says that, right, where the f dash x doesn't exist, that also need to be treated as a critical point. Now see that if I trying to locate at the point if x equal to -1, so let's go ahead. So at x is equal to -1, if I trying to calculate the left derivative, that gives me that we have to substitute -1 here. So therefore we'll see that 3 into 2 minus 1 whole square, that gives me actually 3. And if I trying to calculate the right derivative, we'll find out that at this particular point the right derivative is equal to 2 by 3 -1 whole to the power -1 by 3. So therefore we'll say that at x equal to 1, left and right derivative are not equal. So f dash of 1 doesn't exist. So that means the critical point it's definitely minus 1, not x equal to minus 1 actually, okay. So x equal to minus 1 and 0. So these are the two critical points for this problem. So we obtain the critical points. Now we don't know that at minus 1 or 0, right? Is it local max or local means? Maybe it's a saddle point. We don't know, right? So we have to test it. So what is the test? For the test, we need to use the second derivative test or the first derivative test. But as f dash x doesn't exist some point, right? So go ahead with the second derivative test doesn't gives me a lot, right? So let's go ahead and use that first derivative test. So that's why the easiest way to test it, I take that point. So we'll have minus 1 and 0. Okay, now obviously we need to consider some other point to calculate the second derivative test. So here I consider 1 point here, that's 1.5. I take minus 1.5. I take another point that is 0.5 minus sign, and I consider another value 0.5. So that in that domain we take few points, right, to calculate that what is the value of f dash x at this zone, right? Let's go ahead. So therefore, if I go ahead and calculate that f dash of minus 1.5. Now see that minus 1.5 is actually lies in this interval. So therefore I have to substitute x equal to minus 1.5. So what is the derivative? That gives me 3 into 2 minus 1.5 whole square, and that gives me 3 into 0.5 whole square. Whatever may be, it is greater than 0. If I trying to calculate f dash of minus 0.5, so that particular case is minus 0.5. So that will be lies in that interval minus 1 to 2. That's why you'll substitute x equal to minus 0.5 here. So therefore it gives me that 2 by 3 minus 0.5 whole to the power minus 1 by 3, that's less than 0. So therefore we can say that again we need to calculate f dash of 0.5. That gives me that 2 by 3 0.5 whole to the power 1 by 3 greater than 0. So therefore in this case that at minus 1.5 it is greater than 0. Here it is less than 0. Again it is 0.5, it is greater than 0. So see that at x is equal to minus 1, f dash x changes sign from positive to negative. So that is x is equal to minus 1, it's a local maximum. Oppositely, if I consider that x is equal to 0, f dash x changes sign from negative to positive. That is x is equal to 0 is local minimum. So therefore, we can see that here we are having only two maximum, minimum, and that's it, okay? So we can't skip it here because we don't know that for some problem that minus 1, 0 may be the saddle point. So that cannot be the maximum and minimum, okay? That's it. So, and also secondly, we have going forward in that second derivative test, first derivative test, that is crucial. But obviously here we can understand that by calculating the value as sign changes, so we can easily click for the second option, right? This analysis you not need to be performed, right? Because here not asked that what is max, what is mean, okay? And that's it. Hope you understood the problem. Thank you.